Hi, everyone. So I hope if you all saw the talks from yesterday, one thing to take away from all of this is that I think we all kind of are, in some ways, thinking about the same or at least similar problems. But in the way that we think about them and the way that we solve those problems, um, it's it's very very different based on what you saw in people's talks. And so yesterday I would say it had a more theoretical slant, um, and today I think has a more kind of applied slant. But I don't want to like create that. I really don't like that distinction that happens in science, because I think it's all just different perspectives of how to solve similar problems. So, anyways, this isn't my talk. This is Karianne's talk. Our first speaker today is Karianne Bergen, who comes from Brown, and I'll just let you go right ahead.
All right, is the mic on? Can you hear me? Okay, cool. I feel like I'm under like the spotlight here. Hi everyone, thanks for making it to the early talk in the morning, and thanks to John for inviting me. He actually invited me to give a virtual seminar about 2.5 years ago, and so when I got the email to come in person, I was excited because I feel like usually these virtual talks, nothing ever comes of them. People don't invite you to come back in person, so that was exciting. So I'm glad to be here, and yeah, I'm going to talk about some of the work that my research group is doing. And as John said, I'm based at Brown University. I have a bunch of weird affiliations, but I'm mostly in the Data Science Institute and also the Department of Earth Sciences as well. So let's see. Having trouble getting it to advance. Okay. All right. So if you've heard me give a talk before, I used to do a lot of work in solid earth geoscience, which I'm not going to talk about today, but I used to do a lot of work with like unsupervised earthquake detection, sort of pattern recognition. I've given a lot of talks about machine learning and solid earth geosciences, but today I'm going to talk more about what my group has been doing recently, which has been kind of shifting a little more into climate applications. So this is my research group. We're called the Scientific Machine Learning Group at Brown, and so we're interested in developing machine learning solutions for scientific data in general, because of the sort of students that I tend to work with are coming from earth sciences, so we're mostly collaborating with and working on problems in earth and climate science. And so some of the sort of machine learning topics we're interested in, I'll talk about explainable AI a little bit today at the end. We're also aware in sort of physics-informed learning. I like to think of it as domain-aware learning. I like that term a little bit better because it's a little bit broader than just tools like PINs, which are kind of a popular form of physics-informed learning, but we like to think of it more broadly. I have a couple students who are interested in uncertainty quantification, and we're also sort of starting to look at data-centric machine learning. The sort of applications we're interested in are pattern recognition is a big one, but also today I'm going to talk about surrogate modeling or emulators, which is kind of a theme that we've seen in the conference so far. I've heard a number of others that are working on that, and data enhancement or statistical downscaling. And in terms of sort of the earth science applications, today I'm going to talk about our work with ice sheet models and sea level rise and Arctic sea ice. But in the past, I've done work with sensor networks, natural hazards, extreme events, and we also have some active projects related to kind of New England, sort of coastal oceanography and coastal resilience, which I'll mention but not go into a lot of detail. All right, so I'm going to have sort of two parts to the talk. I'm going to talk about sort of the machine learning and cryosphere projects, where we're using machine learning-based emulators and downscaling. And then toward the end, I'll talk a little bit about our explainable AI work. So I moved these slides around a little bit last night. So to sort of one of the themes that I've seen kind of in the conference and at the posters and from talking to people is this idea of sort of emulators or building surrogate models with machine learning. So the idea is that you might have some sort of a computationally intensive model, something like a physics-driven simulation or some other computationally expensive tool that you're working with to do your science. And the idea is that we want to build a machine learning model that will approximate what that model is doing. We've heard a lot about these examples with emulators for weather forecasting from a number of speakers. So this is kind of a, like in weather and climate, this is sort of a popular example. We talked about GraphCast forecast net. And these are basically emulators where instead of using our sort of mathematical models and physics-driven models of the weather, we're learning to forecast the weather in a purely data-driven way. So this is an example of an emulator. Our emulators are not going to be as expensive. We don't have those computational resources that Google and NVIDIA have for our projects. So we're building smaller emulators. So one of the emulator projects that we have is sort of driven by a problem from our collaborators who are interested in how much the Antarctic and Greenland ice sheets are going to contribute to future sea level rise. And this is the work of my graduate student, Peter. And in this case, the emulator is not going to be one of these weather forecasting emulators, but we're going to be emulating a climate model. And so in the climate model, we have our inputs are these forcing agents. Then there's a number of different modules that are modeling different aspects of the Earth system. And what we're trying to get is some sort of average sea level contribution coming from our ice sheet. So we have all of these different components. And these models are very expensive to run. We don't run them ourselves. There's a sort of community of ice sheet modelers that each group has their own model. But these have to run on supercomputers for weeks. And so what we want to do is try to take these kind of components where the physics is happening and see if we can approximate that with a neural network. So we take the previous model, runs its data, and we want to build a model that maps directly from the forcing agents to the quantity of interest, which is the sea level contribution. So unlike the weather forecasting example, we're not trying to output like a map of the weather everywhere on the globe. We're just trying to get like a single value, basically the sea level contribution, and without doing all these kind of detailed calculations. So we want to get an approximate mapping so that we can do experimentation and exploration into the drivers of sea level change without having to wait a week every time we want to run, or weeks, every time we want to run a new sort of computational experiment. All right, so I think hopefully we're good with emulators. All right, so to get at this question of how much the Antarctic and Greenland ice sheets are going to contribute to future sea level rise, scientists run a series of targeted experiments on these computationally expensive ice sheet models in particular, working with ice sheet models from this ensemble called ISMIP6, the Ice Sheet Model Intercomparison Project. Those different groups are sort of running a shared set of experiments using different ice sheet models. And these ice sheet models are trying to help project the global mean sea level change under different sort of climate scenarios. So there's, on this plot, you see there's sort of spread around each of these scenarios, and those are because there's a number of different models that give slightly different predictions. So we're trying to emulate that ensemble of models. So that's our sort of question, can we emulate these models? We have one paper that we've published on this, but I'm going to talk about kind of our ongoing work. But this is a collaboration with 3 scientists who are all involved in the IPCC, the latest IPCC assessment report in the cryospheric science chapter. So my colleague at Brown, Baylor, Fox, Kemper was the lead author of that, and then our other 2 collaborators are leading experts in Antarctic and Greenland ice sheet modeling. And so we're trying to build an emulator for this ensemble of models in ISMIP6. These models are trying to look at sea level change due to the Antarctic and Greenland ice sheets. So we have a separate emulator for Antarctica, a separate one for Greenland. So we have 2 sets of models. And we're trying to project these for the year 2100, so the end of this century. They just actually ran new data, and they go to the year 2300, but we haven't actually emulated those yet. So that's going to be future work, because that just came out recently. So the previous work in this, the only emulators that existed, there was sort of a simple like reduced order model, and there was a Gaussian process emulator. So that's what we compared to on our initial results. And we used a neural network emulator, so it's still a pretty small neural network. We're using an LSTM, but we're able to better fit the ensemble mean and distribution using an LSTM. In our sort of latest extension of this, we look at distinguishing between different scenarios. So we're looking at, can we distinguish between different emission scenarios? Like, do they actually give different projections for sea level rise, which is something previous emulators weren't able to capture. So previous emulators, like regardless of what we said, we as humans do in terms of greenhouse gas emissions, they were basically making the same projections for sea level rise, which is something that doesn't maybe quite make sense. So we're able to actually distinguish scenarios which the original models are able to. So that was something that was kind of lacking in previous emulators. And so here's just some kind of table of results. You don't need to read all of this, but the purpose here we have kind of in bold where our model, which we call IceFlow, is performing the best compared to Emulandice is the Gaussian process emulator, and LARMIP is another sort of reduced order model. These two were used in the last IPCC assessment report as emulators for these ISMEP6 models, so those were kind of the current state of the art, I guess. And one of the things that we have, this is kind of our nice flashy figure, which is showing that we can actually distinguish the scenarios. So here we have in teal and orange, we have two different sort of sets of models that are different scenarios. So one is sort of a low emission scenario, one is a high emission scenario. And in the initial ISMEP6 model, we can see that there's sort of a difference in projection between those two. There's a spread in the models, but the mean is different. With the previous emulators, we don't actually see a difference, or actually with one of them, the sign is wrong. And so ours does a much better job of sort of capturing the difference between scenarios. And so this is basically updating an existing figure from the IPCC assessment report where they had these other bars, but ours, which is this one, was missing. So, all right. So we're building emulators for this problem. And really where the advantage, because we are doing some exploration of these emulators. We're trying to understand how to build better emulators and why they work well. That's sort of our extension. So one of the things that we found is that the reason why an LSTM, a neural network emulator, works better than something like a Gaussian process is basically because we can give it more inputs. The Gaussian process is sort of limited in, it doesn't scale up as well. We can't give it as many inputs. And so we can give our neural network a richer set of forcings. And so that's able to give us better emulation. So that's really what's driving the performance improvement. In our ongoing work, which we're in the process of kind of rating up, we're looking at quantifying the different sources of uncertainty and exploring model insights. So that's a piece that's kind of trying to connect us a little bit with the physics. So our emulator is pretty far removed from the physics. We don't have a lot of physics built into it. But we are able to sort of look at some of the domain questions. So in terms of quantifying uncertainty, we initially, in our first publication, used a technique called MC dropout. So initially, the emulator that they were using was a Gaussian process, which gives you some uncertainty. And this was because they had an ensemble and they wanted to capture the spread. We're actually modeling each member of the ensemble separately so we can get the uncertainty through that. But they wanted to see some uncertainty. So we used Monte Carlo dropout, which basically generates sort of an ensemble of predictions from a single model. And so that was our initial approach. My student has been working on other methods to sort of separate sources of uncertainty. We've applied it to this, but we're also applying it to sort of machine learning benchmarks. But I don't have any results for that. So in our new IceFlow model, we're looking at sort of two pieces of the model. So we're using density estimation using a technique called normalizing flows to quantify the uncertainty in the data, and then a deep ensemble for the model uncertainty. So our architecture looks a little bit like this. So we have our inputs, we have our emulator variables. We then take those variables, we feed them to a normalizing flow. That gives us an estimate of sort of how sparse our data is in the area where we're making the predictions, so we can get a sense of whether we have a lot of training data that's sort of nearby, and gives us a measure of uncertainty based on sort of the data sparsity. And then we feed this also into a deep ensemble, so we have an ensemble of LSTMs, which gives sort of a different set of predictions, so we get uncertainty from that, and that's the uncertainty coming from the emulator itself. And then we can sort of take the mean of the deep ensemble, and that gives us our actual sort of point prediction. So this is our updated architecture. We call it IceFlow, because we're using ChatGPT to come up with nice acronyms, and that's what we came up with. And so with this project, another thing that we've been looking at is using explainable AI techniques to try to understand, what is the emulator actually doing, so that we can give our collaborators who are not really machine learning people, they don't quite understand how emulators work, what they're doing, to help sort of build confidence and see that the model is doing something that makes sense. So one of the things that we have in our model is that we feed in as inputs to the model the difference between sort of some of the modeling choices that different groups made. So we have an ensemble of models in ISMIP6. Each of these groups might have different choices in their model, and we have a table of these. And so one of the things we did was we looked at, like, if we include those specific modeling choices, does that help us get a better prediction? We assumed that it would, because the model would be able to learn, like, okay, if you initialized your ice sheet model a little bit differently, maybe that's going to result in some sort of change in the kind of predictions you would expect to see. And so we get better results when we include the modeling characteristics. And we can also look at which ones were the most important. And I'm not an ice sheet modeler, so I can't explain to you why these came out in this order. But when we show these to our collaborators and talk them through, they're like, oh yeah, these ones make sense. These are what we think, like these make sense to us. So things like the initialization method. So the models, that one is, they sort of start them at an earlier time. They sort of warm start them. And so the method that they use to sort of initialize the models makes a difference in terms of their final prediction, which makes sense to us and our collaborators. And so on the model resolution, because they have slightly different resolutions and have to be like regridded, that's something that is important as well. So we can look at whether the sort of things that the emulator is using make sense. So that's something that our collaborators like. And another example of some of the kind of exploration that we were doing is looking at whether you can emulate using surface air temperature or surface mass balance alone. Our collaborators were like, we think that this is all you need. So we wanted to look at if additional forcings improve performance. So we both ran it like with all of our forcings and then just temperature and just surface mass balance. Those are related to each other closely. I'm told, I'm not an expert again on ice sheets. So those are quite similar to each other. The idea is that you could use just one or the other. But we find that we do get better results if we include additional forcings as well. And again, we can sort of look at how much each of these forcings is coming into play. So we find that even though surface air temperature and surface mass balance are sort of the most important, our model is taking advantage of other forcings as well. All right, so that's this project that's kind of ongoing. We have a more kind of machine learning focused paper on the uncertainty piece that's coming, but I'm focused today on the science. So, all right. So I have another project that we're doing also related to sort of cryospheric science, working with another graduate student who's interested in how the changing climate is going to impact the navigability of the Arctic. And so the idea is that, as the climate changes, the ice in the Arctic is going to melt, and we may be able to navigate the sea routes in the Arctic for longer periods of time throughout the year. So this is a plot that's showing kind of the Northwest Passage, a route past Canada, and then the Northern Sea Route, which runs along the coast of Russia. And this is something that could be of geopolitical importance if these sea routes suddenly become more accessible throughout the year for shipping. This would obviously impact the sort of geopolitical importance of Canada and Russia, respectively. And so for these, one of the challenges, though, is that these straits, where you would actually navigate through, are quite small, and they're smaller than the resolution of climate models. I have a colleague who's also looking at similar problems in the South Pacific, where the islands in the South Pacific are smaller than the grid boxes in climate models. So we have all these problems where we're interested in what's going to happen in certain locations, the impact of climate change, but the things that we're interested in are too small to resolve in the models. So this is kind of zooming in on this particular strait. We can see these are roughly the points that are resolved in the CMIP6 models, which are the climate models that we have. And you can see that the spacing is sort of too large to really be able to kind of say what's happening in these individual straits. So we're interested in seeing if we can use machine learning to downscale our climate model data to a resolution where you could look at sea ice in these particular straits. And so downscaling is trying to map from low resolution. So here's our strait, and here's sort of a low resolution map. This is coming from ERA 5 data, because we have higher resolution data for that. So we've tested this as a proof of concept on ERA 5 data. It's going to be future work to actually do it with climate model data. We start with low resolution data, and then we want to map to higher resolution using machine learning. So that's what we're doing here. And so here we want to map from We have 1 degree resolution in the original data. We want to go to 0.25. That's roughly 100 kilometers to 25, but in the Arctic, the grid's a little bit wonky, so we'll stick with degrees. And so our method here we call ICE-GAN. This one is very convenient. Ice Concentration Enhancement GAN is what that stands for. So we're downscaling with a GAN. It takes in sea ice and some other climate variables as inputs. It takes sea surface temperature, snow depth, sea ice convergence, and surface heat flux. So a series of different inputs. And we feed this into our super resolution GAN, and we use we have a constraint layer, so I'll talk about that in a minute, of an adversarial loss with the GAN, and so we get a high resolution output. So sort of a standard approach. The one difference in the approach from kind of a standard GAN is that we use a hard physics constraint, that the amount of sea ice locally has to be conserved. And so the way that we do that is basically, it's pretty simple, is on the output you might have like a grid, and we know how much ice was originally in this grid. And so we basically, at the end, rescale it so that it ends up being sort of the same amount. And so we rescale it using this sort of softmax normalization. We tried different normalizations. This one, in practice, worked the best. But it's a hard constraint. So we basically can't have ice like disappearing or appearing where it didn't exist, or the amount changing sort of locally. And part of the reason for that is to make this more robust under a changing climate. This is one of the challenges with a lot of these climate problems, is that it's hard to test how well these methods are going to generalize under climate change. And so when we put in a constraint like this, 1, we get better performance. 2, it sort of puts a limit on how badly it will generalize. It's not going to do any worse than the current state of the art, which is nearest neighbor interpolation. So the current methods for this approach are nearest neighbor and bilinear interpolation. And we outperform that. We also do better with the, here I have SR CNN. That's basically the same architecture without the adversarial loss, so not sort of the GAN setup. And here's just like one of the plots. We have a lot of plots that we generated in the paper. This is during sort of the shoulder season, which are the ones that are where the amount of sea ice is sort of changing, or it's not just solidly either ice everywhere or no ice. And so we can see the nearest neighbor and bilinear do very poorly. The errors are pretty high. We do better with our CNN, but then with the adversarial loss, it does better. So this is ours here. Oh, sorry, I have the cursor on my screen you guys can't see. All right. And then if I show kind of what the outputs actually look like, because these are the errors that are plotted, the low resolution data for this particular case is over here. We can see that it looks really bad because like the scale of this, it doesn't resolve these sort of patches of land. So around where you have land, you get these kind of weird results where it doesn't quite know what's happening. And so the high resolution data looks like this. We sort of masked out the pixels that have land in them. And so we get a pretty good result with our GAN. It's not perfect, but as we can see here, it's a lot better than our interpolation methods. All right. And so in terms of our kind of work with downscaling emulators, we have a number of projects related to this, and both of these are somewhat related in some cases. So I've sort of grouped them together in terms of the kind of things that we want to do. So one of the things that we're interested in looking at is what's kind of data quantity and quality we need in order to capture extreme events. So we have some other emulator projects we're interested in what's going to happen in coastal New England, where storms are going to impact sort of coastal flooding, and so those are kind of extreme events that we would need to be able to model. And we don't have as many examples of those, so that's one of the questions we have with emulators. And whether we can emulate or downscale from sparser inputs. So in some cases, we have point observations rather than data coming from models. So we have some questions on sort of the data side we're interested in. On sort of the architecture side, we're interested in this question of like, what are the actual, when we're building emulators, which are the physical principles or domain knowledge that we need to include? So for example, in our downscaling, we included our sea ice conservation, but no other physics. We included some physics-based variables, but we didn't have any other direct physics other than our kind of local sea ice conservation. And in order to ensure that we're going to be able to generalize under climate change, because that's one of the big challenges with any application of machine learning with climate. We just don't know how well it's going to generalize. We can often try to like look at past data and see how well it generalizes to sort of more recent years with some small amount of change, but it is hard to know like with future climate change as you get more extreme how well these things will generalize. And then there's also some questions that we are interested in about how do we represent, kind of separate out the local information versus kind of global information so that we can better make models that will generalize across different regions. And so this is something where we're interested in. There's sort of links to foundation models and like retraining models, fine-tuning them for downstream tasks. So we're interested in some cases we have limited samples and we want to build a model that we can apply in different locations. So like for the downscaling, right now we're just downscaling that one particular strait, but we want to be able to generalize it to larger regions. And so how we can learn in those kinds of cases. We also have some projects related to this that are part of another effort that's looking at coastal resilience in New England. So this is a big collaboration, and so the AI piece is just one component, but we're interested in data-driven models for downscaling, getting local climate information. So we're doing some downscaling emulators for this project. And one of the things we're interested here is looking at can we repurpose some of these kind of AI-based weather forecasting emulators, sort of treating them as foundation models and then sort of fine-tuning them to do local tide forecasting. So that's kind of one of the next directions that we're looking at with these. So that's kind of we have a number of different projects related to this. These questions around emulators and downscaling. And I guess I'll go to the next topic, and then we'll take questions at the end. It's sort of awkward when there's like two parts of the talk. So the other set of projects that I want to mention briefly, this is more on the method side and not specific to geosciences, is explainable AI for scientific data. And so we were part of a collaboration called the Scientific AI Center, which is funded by the Office of Naval Research, to look at basically how to study sort of the science of AI and also look at how we can use AI better for science. So we have kind of both sides. And the part of the effort that we're leading is looking at explainable AI and particularly building intrinsically interpretable explainable AI methods. So a lot of explainable AI, you like build a model, and then after the fact, you try to probe the model, which we did with the emulator paper, to kind of try to understand what the model is doing. Those techniques have some problems to them, like depending on which technique you use, you get a different explanation oftentimes. So we're interested in building architectures where they're designed to give certain kinds of explanations in a way that's more straightforward. And one of the challenges with doing this is that anything with explainable AI, this is a topic that's challenging because it's hard to define mathematically. So in AI and machine learning, if you want to solve some sort of a problem, you have to sort of be able to define it like mathematically as an optimization problem. And that's hard to do with a concept like explainability or interpretability. And so it's also challenging because for every problem, your explanations, you may want a different form of explanation, or depending on who's the person who's going to be receiving the explanation, they might want different information. And a lot of the work in explainability is like, can we extract some sort of equations or some sort of a physical parameter? But not all domain knowledge sort of takes that form. And so the kind of explanations we're looking at are what we'd call instance-based explanations, where explanations are basically we're explaining based on specific instances that have been observed and using those as sort of references. So we're going to compare the predictions to like specific examples or cases. And this is something that makes sense not in every problem, but it makes sense in a lot of scientific disciplines where the similarity between different cases is important. I used to work on a lot of problems in earthquake detection, and one way to detect earthquakes is with template matching, and there you say like, these two earthquakes look alike, so I have this one, I know what it looks like, this other one's similar, so I'm pretty sure these are earthquakes happening in the same location. That's where you have sort of these instances make sense. There's a lot of scientific applications where similarity to past cases is a useful way of reasoning. So that's the approach that we're taking. And so we try to build our architecture so that we can give these sort of instance-based explanations. And so we're trying to develop new techniques using prototypes. So this is kind of a class of methods, although it's a somewhat small class of methods. And the idea with prototype-based methods is that we build in to the model a set of sort of prototypical instances, and the model has these it learns these from the data. It sort of selects what are the best prototypical instances, and they're part of the architecture, so the final decision is based on how similar your new example is to these prototypes. And so that's sort of how the final decision is made. So your explanation will take the form of like this 3. We know it's a 3 because it looks like this prototypical 3. It's this sort of form of explanation that we get. And so we've been looking at these kind of methods and extending the different types of methods. These have mostly just been developed for images, so we're interested in looking at them more broadly. My postdoc was looking at whether we can get additional information from our explanations. So rather than actually having fixed prototypes, she trains a model so that in the latent space, basically our data are somewhat clustered. So we can sample data and use anything from the class as a potential sort of sampled prototype. And this allows us to generate multiple predictions and multiple explanations, so we can then explain sort of ambiguous cases or uncertainty. So we get an ensemble of predictions. Each time we have slightly different prototypes we're using as references. And so this is sort of an interesting approach that she's developed. So in this case, rather than having a single sort of fixed set of prototypes, we draw these, we sample them. But otherwise, we keep the architecture similar to a more traditional prototype-based method that have fixed prototypes. But what this does is, so she's applied this to a data set called Fashion MNIST. So it's, if you've heard of like the MNIST data set, this is the version with fashion stuff. So it has like shirts and boots and things like that in it. So this is a test case where we have this ankle boot is the correct class. And our model was correct 100% of the time. But what we can do is we can say, like, these were the specific examples that look the most like it. And so that's how we know that we're confident, is based on like the high similarity of these cases, and that basically no matter which of our data we sampled, it was always most similar to the sort of ankle boot example. And so this is not just an explanation after the fact. This is like actually the reasoning of the model itself. It's saying this is an ankle boot because it's very similar to these and not as similar to the other examples that were drawn from the data set. And when it gets for difficult cases, so this is a coat. The low resolution makes it a little bit hard to know if this is a tricky case or not, but for our model, it's kind of roughly, kind of evenly split between a coat and a shirt, which I think makes sense. I can't tell which one it is from looking at it. But we actually can get an explanation for why the model was unsure. So in the cases where it predicted coat, it was predicting coat because it thought that this coat here looks more like this coat than this shirt. And it looks more like this coat than this shirt. When it got it wrong, we know it got it wrong because this coat looks more like this shirt than the coat there. So we have these sort of examples of like where it's making the decision and why it's unsure, using specific examples. So that's kind of one of the things we're doing. Again, we haven't tested this on geoscience data. This was just a paper focused on explainable AI, but we have other extensions we're looking at. So one of my students is looking at building these methods for spatiotemporal data and applying it to spatiotemporal forecasting problems. So she's developing this method and testing it on looking at the phases of the Madden-Julian oscillation as sort of a test case. There's existing literature that look at prototypes that have certain spatial locations. So they're looking not only at like, do these look similar, but where are they, which is important in geosciences. So this actually, previous paper looking at spatial locations was developed by geoscientists, because a lot of times in geosciences where things happen matters. And we're trying to extend this to also include a temporal component. And so that's work in progress, so I don't have any like plots of that to show. We're still working on it, and we have a number of different directions as well. But we're trying to look at kind of both key spatial and sequential information to be able to sort of explain how something is evolving over time, basically. Yeah, so that's all I had. And I'm happy to answer questions about kind of either any of these different projects.
So who has questions for Karianne? Yes, Anders.
Thanks, and thanks for a very interesting talk. I was just wondering about this, the last type of method you mentioned now, using the prototypes. How does that react to adversarial type attacks if you sort of make very small adjustments to the pictures?
We haven't tested it for that. I think most of these techniques are not necessarily, I haven't seen any prototype papers that have really looked at that. So I don't know.
Yes.
Yeah, thanks, Karianne. So I have a question about the first part of sea level rise ensemble predictions regarding the uncertainty quantification. So I was wondering, is there a good way to distinguish the spread of the uncertainty as a result of the different forcing in the actual model versus the neural network uncertainty itself?
Yeah, so that's meant to be the next steps of the students project. I don't know. Right. I feel like that's been supposed to be the next steps for a while, so I don't know when we're gonna. But we were looking, one of the things we're interested in is looking at like which of the particular features contribute more to the uncertainty. There aren't a lot of methods that are kind of trying to explain uncertainty other than just like the model and sort of data uncertainties. So there's not a ton of techniques like looking at splitting those, but we do want to look at like whether the idea was like to try to see if we could take some of the feature importance techniques and sort of apply them to the uncertainty as opposed to like the prediction decision, but we haven't gotten to that yet.
For the downscaling example, I was just wondering if you could explain a little bit more what your ground truth there was.
Yeah, so for this case, the ground truth is coming from ERA 5 data, which we have the higher resolution, and then we coarsen it. So this is mostly right now testing the sort of proof of concept. So we coarsen it to the same resolution that you would have in like the CMIT models, but we don't have, to actually do it with the CMIT models, it's hard because we don't have the high resolution. So you'd either have to run like a regional model, which I don't think we have for that area to get higher resolution, or you would have to use some sort of observational data in order to kind of extract that information.
So is this AR5 thing, is that a model or is this satellite-based observations or something?
AR5 it's the reanalysis data. So that's like the same data that's used to train like the weather forecasting emulators. It's kind of like the closest we have to the ground truth for like the sort of like weather type variables. And so it has some of these sea ice related things in it. But it's combining model and data, like it's assimilating observations.
And then there's some sort of time series in there that gives you then confidence that the dynamics are reproduced by that downscaling.
So right now we're just doing the downscaling at like single time sort of snapshots. We don't have any temporal information, although one of the variables that we find is really helpful is sea ice convergence, which that's like looking at how the sea ice is like the dynamics, how it's changing over time. So I think that it would help to have the temporal information, but so far I don't have anyone to sort of pick up this project. The student's like now working on something else, like a different grant got funded that she's gonna work on. So that's like another thing that we could look at that I think could be interesting is like downscaling and looking at the temporal component. But we didn't really look at that. But I think it would help.
Were there more questions? Oh, Omar. Yes, of course.
Karianne, about the ice sheet problem. So you had a slide there that had a list of, looked like a dozen or so parameters that were inputs, right? And then you said there are 11 other or something characteristics of the model. Where does the basal friction show up? It's an infinite dimensional field. That's uncertain. So is that that's not part of the input, it doesn't look like.
No, so we're taking the climate, so we're using the forcings that are the same forcings that go into the ice sheet models, but we don't have like the ice sheet model characteristics. Those capture like what's happening within the ice sheet models and the things that would like differentiate them. So I don't know a lot about the specifics of the ice sheet models. We're sort of treating them as like, we have our ice sheet model experts on the team who are kind of telling us if we're using the data correctly, but we're kind of viewing these as like there's a team of people, they all develop their own sort of black box that takes these inputs and produces that output. And so I don't know about that particular, like where that's coming in, but it's not an input that
Not an input.
it's not an input that we're
the
using. So the inputs are coming from CMIP6, and they take those and they input them into SMIP6. That's part of why they want emulators, because they have to wait until all the other, like the climate models are run in order to then run their models on the outputs of like the other climate simulations. And so for the IPCC, they like want to have the emulator results so they can start kind of writing things up before they're actually, while they're waiting for the simulations to run, in a sense. Like they're sort of guessing what the results are going to be while they're waiting for them, because they get their results kind of late, is the impression. This is my understanding. Again, I'm not an ice sheet modeler, so.
Because there's a lot of uncertainty in the basal friction,
Yeah.
geothermal heat flux, the basal topography, and these are all infinite dimensional fields. And
Yeah, so there's,
question of
oops.
how you
Okay, I
scale
think
up.
I messed up this. And there's some of those are probably in the,
The list of 11 that
List.
you had there, ISM, is that
Yeah.
SSM? Is that Helen's ice sheet model that you're using?
yeah, so they have things like basal melt sensitivity to ocean forcing. So these are characterizing like differences between different ice sheet models. So like different modeling groups are making different choices with respect to these. So if there's something where they're all making the same choice, that just goes into like the black box we're trying to emulate. So we're a little bit far removed from the physics, aside from like we have the inputs, like the forcings, and then we have the differences between the models that we're characterizing. So we might see that like if models choose a specific initialization method, maybe all of those are getting slightly like higher estimates versus ones who are using a different one, like the emulator would capture that. So that's why we get better results when we include these. But I don't know the details of like all of these. I would have to have either ask my collaborators or my PhD student. He dug into this a little more, but I don't know exactly what all of these are doing exactly.
Right.
Sorry.
Thank you.
Okay, well, let's thank Karianne for her talk.